One of the most common ways to construct trial wave functions for variational theory is to take our trial wave function and make it out of other functions, often solutions to other problems or things like that. And so we use a linear combination of other functions where our trial function looks like some constant, C1, times our first function, plus some constant, C2, times our second function, and we can add as many functions as we want, or as much as our computer can handle, or whatever. And so we can generalize this and say that our trial function is equal to sum n equals 1 to however many functions we want to include of coefficients times functions. And the parameters we're going to vary are these coefficients. And we will vary these such that we will get our lowest possible energy from this trial function. So this is we're talking very generic here, right? And so maybe your functions here are solutions to the hydrogen atom to start with, or or something like that. So we'll look at the generic case and how we would go about doing this in a system. So we'll look at just two parameters to keep things simple. So we have two functions, f1 and f2, with their coefficients c1 and c2. And so things we're going to have to define are, to find the energies, we need to write out our integral that goes on top here, right? So our expectation value for the energy. And if we write this out, this will be c1 squared h11 plus 2 c1 c2 h12 plus c2 squared times h22. And let's define what I mean by these h11, h22, etc., etc. So hij, and this is a generic notation used throughout quantum mechanics, is equal to the integral of function I times the Hamiltonian operator, function j, and we're missing a star here. That should be a complex conjugate, d tau. And we'll look at this next definition in just a second, but the Sij, these are also integrals, but without the Hamiltonian in the middle. All right, and so this is a shorthand notation, so we don't have to write out these integrals over and over again. So the other one we're going to have to write out is the normalization integral, the integral of phi star phi d tau. And that will look very similar, but with the s's instead of the h's. So we'll have c1 squared s11 plus 2c1 c2 s12 plus c2 squared s22. And we call these H1, Hij, and Sij, we call these the matrix elements. So if we want to find our energy, our trial energy, it's going to depend on our two coefficients, and that's what we want to vary. We want to vary those to find what's the best possible energy by finding the lowest energy. And that'll be equal to our two integrals. So we'll have c1 squared h11 plus 2c1 c2 h12 plus c2 squared h22 divided by almost the same thing but with s's. All right, and so this is our energy, but we want to minimize this. So to minimize this, we take the derivative of the energy with respect to each of these coefficients and set it equal to 0, because we want to find the minimum energy. And to find the minimum or maximum of any function, we take the derivative set equal to 0 to find where we have that point where the derivative goes to 0 that corresponds to a minimum. So I'm going to skip a few steps here, but we can show if we're minimizing this using these derivatives, we'll get a set of equations that looks like this. We'll have c1 times h11 minus es11 plus c2 times h12 minus es12 equals 0. And our second equation that will describe our solution is c1 times h12 minus es12 plus C2 times H22 minus E S22. So again, skipped a lot of steps to get there. Now this will only give us a non-trivial answer for C1 and C2 if this determinant, which we call the secular determinant, I don't know why, not sure where that terminology comes from. I guess it's not a religious determinant. But if this determinant H11 minus E S11, H12 minus E S12, H12 minus E S12, H22 minus E S22, if this determinant is equal to 0. So anything else gives trivial solutions. So things like where the wave function is just equal to 0. And so we can solve this. We solve this equation here to find what's the energy.